Welcome to this presentation on the role of functionality in quality attributes, presented by DeepLearn. Now, let's discuss functionality. Functionality is the primary quality attribute as it defines a system's ability to perform its intended tasks. It encompasses various elements, including validity, ensuring outputs are correct, correctness, meeting specifications, interoperability, working with other systems, and security, protecting against threats. For instance, in an e-commerce platform, the functionality must allow users to browse products, add them to a cart, and securely check out. This initial functional decomposition is crucial, as it influences all subsequent quality attributes. If functionality is flawed, how can we expect other attributes to succeed? This raises an important question. How do you prioritize functionality against other quality attributes in your projects? Interoperability is the ability of a system to operate with other systems, including those not yet known or developed. This quality is vital in today's interconnected digital landscape. Consider a health information system that must share data with various hospital networks. If it lacks interoperability, critical information may not be communicated, jeopardizing patient care. One strategy to enhance interoperability involves adopting standard communication protocols, such as RESTful APIs, which facilitate seamless interactions. But what happens when new technologies emerge? How can we future-proof our designs to ensure ongoing interoperability? This challenge is an essential consideration for architects. Security is paramount in software architecture, encompassing the mechanisms that ensure only authorized users can access the system while safeguarding against malicious attacks, such as denial of service. For example, a financial application must employ robust authentication measures to protect sensitive user data. The implications of security extend beyond mere functionality. They can directly influence how we design the system. If security measures are overlooked, we may face critical vulnerabilities. Thus, how do we balance security requirements with overall system performance? This question prompts us to think critically about our architectural decisions. Performance refers to the responsiveness of a system, including how quickly it can process requests. This attribute is often measured in terms of latency and throughput. For instance, a web application must load quickly to provide a satisfactory user experience. Factors influencing performance can be architectural, how computations are distributed across components, and algorithmic choices made in coding. Interestingly, performance often involves trade-offs. Optimizing for speed may compromise other attributes like security or modifiability. How do we navigate these trade-offs in our designs? Understanding these relationships is crucial for creating efficient systems. Resource efficiency, a critical aspect of performance, focuses on how well a system utilizes its available assets, be it memory, processing power, or network bandwidth. For instance, an overly layered architecture may hinder performance by introducing unnecessary complexity. To enhance resource efficiency, architects can employ techniques such as caching frequently accessed data or optimizing algorithms. This leads to a crucial realization. How can we ensure our architecture remains agile and efficient as systems scale? This is a vital question that requires continuous evaluation and adaptation of our designs. Modifiability refers to the ease with which a system can adapt to changes, whether adding new features or fixing bugs. A well-designed architecture allows for growth without extensive rework. For example, consider a social media platform that must frequently update its features to meet user demands. If the architecture is rigid, implementing these changes can be time-consuming and costly. This raises a thought-provoking question. How can we design systems that not only meet current needs, but are also flexible enough for future innovations? Emphasizing modifiability during the design phase can lead to significant long-term benefits. Availability measures the proportion of time a system is operational, while reliability indicates its ability to function over time without failure. These attributes are essential, particularly for mission-critical applications. For instance, consider an online banking system that needs to be available 24/7. Architectural choices, such as redundancy and failover strategies, play a crucial role in enhancing these attributes. How can we ensure our systems are not only available, but also reliable under stress? This question highlights the importance of strategic architectural planning. Usability encompasses how easily end users can interact with a system. A user-friendly interface is essential for ensuring user satisfaction and productivity. For example, consider how intuitive navigation can significantly enhance the user experience of a mobile application. Employing user-centered design principles, such as usability testing and feedback loops, can help architects create more accessible systems. But what happens when users are not the only stakeholders? How do we balance the needs of different user groups, including maintainers and operators? This complexity underscores the multifaceted nature of usability. Quality attribute checklists serve as vital tools in ensuring that all necessary attributes are addressed during the design and development phases. They allow architects and auditors to verify that requirements capture the nuances of specific quality attributes. For example, compliance with the PCI standard for financial systems ensures that sensitive data is handled securely. These checklists not only facilitate regulatory compliance, but also assist in uncovering potential gaps in design. As we consider our projects, how can we develop and refine these checklists to better meet our quality goals? This is essential for continuous improvement in our practices. Thought experiments are a powerful tool for architects, enabling them to explore the implications of different design choices in a hypothetical context. By mentally simulating scenarios, architects can identify potential issues before they arise. For instance, consider a team discussing the trade-offs between a microservices architecture versus a monolithic design. Through a thought experiment, they can evaluate how each choice affects scalability, performance, and maintainability. What techniques can we use to ensure our thought experiments yield actionable insights? This approach promotes a proactive stance in architectural decision-making. In conclusion, quality attributes are foundational to the success of any software system. They encompass various aspects, including functionality, interoperability, security, and usability, and must be integrated throughout the development lifecycle. As we look to the future, emerging trends in quality attribute modeling, including machine learning and automated analysis tools, promise to enhance our understanding and management of these attributes. How can we leverage these advancements to improve our design processes? This ongoing exploration of quality attributes will continue to shape the landscape of software architecture, guiding us toward more robust and resilient systems. Thank you for your attention, and I look forward to our discussion. Thank you for watching this presentation.